Alright, everybody. So I wanted to have this for our quiz, which is tomorrow. I want to remind you that the quizzes, unlike last semester, we don't have drop quizzes because I just have the 4 quizzes. Remember last semester we had a whole bunch of quizzes. That was sort of a different model. So the quizzes are important. That said, 100% on the quiz, right? Like you should be making 100% because you know which questions are going to be on the quiz. There are a lot of them, so there's a lot to practice. I know that might be overwhelming, but with work, you can make 100%. And doing that on the quizzes will help you on the exam. It will help you a lot, in fact. So it's going to cover Chapter 2B. That's the latter part of Chapter 2, and that's only going to cover capacitor circuits. So I didn't put any things about this whole thing where you have C kappa epsilon naught A over D, because that was on our exam, wasn't it? But yeah, so none of that stuff. It's only going to be on circuits. And I'll show you some examples. I think there are 4 circuit questions that are either numeric or qualitative, meaning that there are numbers associated with it or not. And you have to describe something about that circuit. I'll show you some examples. I'll show you the first 3 questions on that quiz. And then Chapter 3 also. And then there are 5 or so questions on this. That has to do with measurements. Ammeters and voltmeters, how do you hook them up, that sort of thing. What do they measure? Current, Ohm's law. Resistance, that's this whole R equals rho L over A. Let me look at the topics right quick. And then power. Yeah, so power. So it's those topics. As you go through the old exams, you'll see that. So somebody had asked, is there any other stuff? Like, for example, if you get into things that are about, what was it called? Internal resistance of batteries and things like that. On the exams, I'll show you as we go through. But if you get into stuff like that, that's not on the quiz. That gets into Chapter 4, not Chapter 3. Okay? So are there particular questions, or can I just start by showing you the first 3 questions on the quiz? I'm going to show you the first 3 questions on the quiz. They're going to look a lot like number 3 here. Like where you have a series of questions, I give you a circuit. Actually, that's not a good example. Let's go down. Yeah, this is spring 18, and number 4, 5, and 6 are good examples. I think I actually give you only 2 circuit questions that use the same circuit, and then I go to another question. So you'll have a series of questions that'll be about the same circuit. Again, this is spring 18. So I want to know, what is the equivalent capacitance of this circuit? That'll be question number 1. Not this question, but something very similar to it. And what you do is you start with a portion that is either purely in series or purely in parallel. Now I have a 3 and a 6 in series. Let me remind you the rules that we have before we start doing this. So for caps in series and caps in parallel, we have these rules. For caps in series, 1, they have the same charge. For those in parallel, they have the same voltage. 2, the equivalent is equal to 1 over C1 plus 1 over C2. 2 over here, the equivalent is C1 plus C2. 3 is the same for both. It's just Q is equal to C times V. Ditto over here. And then 4 is V equals V1 plus V2 plus ... And then there's not really a 4th rule for those in parallel. There is, but it's not useful. So those are our 4 rules. So if I have 2 capacitors in series up here, and I want to find their equivalent, I have a 3 and 6. You already probably know what that is, right? What is it? That's 2. 1 over a third plus a 6 is equal to 2. So this is 2 microfarads. I find that it's really useful to redraw these circuits. You'll have time to do so on the test tomorrow, the quiz. So I'm going to go ahead and redraw it. This is the same circuit, 4 microfarads. This is now 2 microfarads, 2 microfarads, and 12 volts. Okay? Now, I want to know what is the equivalent of these two 2 microfarad capacitors. To find the equivalent of capacitors in parallel, I just add them up. So the equivalent of that is 4 microfarads. So now I'm going to redraw this as a 4 and a 4. Those are in series. And then the final equivalent capacitance will look like this. It is what is a 4 and 4 in series? 2. 1 over a quarter plus a quarter is 2 microfarads. I know that's fast, but we've been doing those in class, and you'll see similar things. I like to use the same numbers because, honestly, I don't really care that you can do the numbers right. I want you to know, how to do the circuits. And this is all 12 volts. Now, so the answer here is 2 microfarads. In the next question, I ask, what is the voltage across the 2 microfarad capacitor? So what is the voltage across this capacitor in that original circuit? Now, that's when I can start stepping back. I know that if I have 12 volts here, what voltage do I have on those 2 4 microfarad capacitors? 6. I have 6 volts here and 6 volts here. I know that because those 2 capacitors are identical and they're in series. Since they're in series, this rule holds that the sums of those voltages have to equal to the total voltage, which is 12 volts. 6 plus 6 equals 12, and they're the same because the capacitors are the same. That means that I have 6 volts here, and then I have 6 volts across this entire thing, that entire parallel branch. Now, capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitor. So if I have 6 volts across this whole thing, that means I have 6 volts across each one. So that 6 volts is shared by each of these capacitors. So I have 6 volts and 6 volts, which is the answer to the question, which is 6 volts. Okay? So C is the right answer. What is the charge on the 3 microfarad capacitor? So I want to know what is the charge on this capacitor. How am I going to go about finding that charge? Yep, Brooks? That's right. Capacitors in series have the same charge, and they have the same charge as their equivalent capacitor. So these 2 capacitors have an equivalent that's here. Whatever the charge is on this capacitor is the same here and here. And this charge, Q equals CV, 2 times 6 is 12 microcoulombs. So I have 12 microcoulombs here and 12 microcoulombs here. Let's write that in. I have 12 microcoulombs there. So that means I have 12 microcoulombs here and 12 microcoulombs here. By the way, now I can figure out what is the voltage. That problem didn't ask for it. The answer is 12. But if I wanted to know the voltage on the 3 microfarad, the voltage would be Q divided by C. 12 over 3, that would be 4 volts. 12 over 6, that would be 2 volts. Notice the 4 and the 2, they add up to equal to the 6, which is on that equivalent capacitor. So you'll have a series of 2 or 3 questions that will be like that. We can do another example in a bit, but I want to look at some of the other stuff as well. The other type of question that you're going to have, actually you have 2 questions that use the same circuit, that just like this, and then I'll give you another question that's a different circuit, okay, that's asking a similar question, what is the voltage or the charge or whatever. They're all a similar difficulty to these. The other thing that you'll have, let's see if I can find an example, is sort of like this one right here, where you have capacitors but no values. And this sort of freaks students out. But don't let it freak you out, because you're still doing it the exact same way. So on this one, I want to know the voltage across C1. I'm not saying it's this problem. There are other problems that are similar to this. But I want to know the voltage across C1. So what I do first is find the equivalent capacitor. I have C there. And here I'm going to have 2C. And I have 12 volts. Look, we've worked this problem a bunch of times. This is like the 3 and the 6 microfarads in series. So if I have a 3 and a 6 microfarads in series, I know that one of them has a voltage that's twice the other. And then also that those two voltages have to add up, in this case, to equal to 12. So I know that my voltages are what? What and what? 8 and 4. Those add up equal to 12. They're twice the other. But which one gets which? Which gets 8 volts and which gets 4? C gets 8, and the 2C gets 4 volts. Big capacitors get small voltages. Small capacitors get big voltages. They have an inverse relationship. So I'm looking for the voltage across C1. That's going to be 8 volts. By the way, if I want to know C2 and C3, that's pretty simple. It's going to be 4 volts and 4 volts. Okay? So you'll have one like that. It'll be similar to that, where you have a circuit but with no numbers. It helps you to sort of think about how those voltages are distributed without just reverting back to, the equations. You'll have some questions about ammeters and voltmeters, kind of like this one. There are a couple things that you need to remember. We went over these in the notes, but voltmeters you hook up in parallel or series. Parallel. Voltmeters are hooked up in parallel. Ammeters are hooked up in series. Voltmeters, of course, are used to measure voltage. Ammeters are used to measure current. And then voltmeters have a big resistance, and ammeters have a small resistance. We've had a lab. Not all of you have done that lab, but it was also in the notes. So for number 10, for example, the resistance of a voltmeter is big. True. The ammeter is connected in series. True. The voltage across an ammeter is small. True or not? Is that a true statement? Remember, ammeters have small resistances. They have tiny resistance. In fact, the resistance of an ammeter is basically just a piece of wire that you're adding in. And so if I have a really small resistance, I'm going to have a small voltage. So the voltage across an ammeter is small. True fact. The resistance of an ammeter is small. Is that true? Yeah, that is true. So here the answer would be all of these are correct. Let's return back to this statement right here, because that's the one that trips you up. And that's also the one that tells the difference between B and E. B, which is incorrect, and E, which is correct. Imagine that you have a circuit like this. I have a resistor, and I have my ammeter. If my ammeter has any resistance at all, then it's going to have a potential across it. Right? But an ammeter doesn't have any. It's a tiny, insignificant resistance. And this also has a voltage, but you want your ammeter to be like it's not even there, like you don't even see it there, because in general, when you do measurements in any system, you don't want to affect the system. So the voltage here has to be basically 0 across the ammeter. Okay? So the voltage across an ammeter should be really, really small. You'll have one like that. You'll have not like this, no electromotive force. But you could see something like number 4. This is Ohm's law. Ohm's law, it'll be a pretty simple application of Ohm's law. V is equal to IR. All right, so that's pretty straightforward in this case. My V is 12 volts. My I is what I'm looking for, and R is 3 ohms. So that means that I is equal to 4 amps. This is also asking about the conventional direction of the current. I know it's not C or D, but is it clockwise or counterclockwise? What direction does the current go? Clockwise or counterclockwise? Very good. Y'all did your notes last week, didn't you? Very good. My 151 class, not so much. Like we did the same thing, but y'all are much better students than they are. Don't tell them I said that. Some of them are very good students, in fact. All right. So this conventional current, which is the current that we would say protons would go, there, a throwback to Benjamin Franklin, would be clockwise. It always comes off of the big side of the battery and goes in that direction, away from the big side of the battery. So that's another question that you'll have, an Ohm's law question. So far we have 4 circuits, 3 which are quantitative, 1 which is qualitative. You'll have a What is the other one I did? Oh, ammeter or voltmeter question. That's number 5. Then you'll have an Ohm's law question. Then you'll have a resistivity question, like number 18, for example. You're going to have a question like this where you have to identify the unknown material. They're on every test, so try different ones and make sure you get them right. Once you do them a couple of times, you'll see that they're pretty simple. What you want to do here is calculate the resistivity. R is equal to rho L over A. So I solved this for rho, the resistivity. That's going to be R A over L. R is, I'm sorry, you have to solve for the R. So I have to find my R. I say that V is equal to IR. R is equal to V divided by I. V is given, that's 20. I is 10. 20 over 10, that's 2 ohms. So I have 2 ohms is my resistance. The area, which is given, 5 times 10 to the minus 8, divided by the length, in this case is 1 meter. So that's 10 times 10 to the minus 8. That is going to be iron. I can tell because it's 10 times 10 to the minus 8 ohm meters. And then I just go through the table and I find the one that matches up with that answer. That'll be one of your questions as well. Identical to that, just different numbers from one of the old tests. There's one in practically every exam I've ever given. You'll also have a power question, not necessarily like this one, but one where you're utilizing this idea that the power is equal to V times I. So not necessarily a question just like this, but a question having to do with power. Power is equal to the voltage times the current. Here, there are a couple ways that you could do this. I'm given the voltage, which is 3 volts, and the resistance, which is 10 ohms. And I want to know what power is dissipated. Power is equal to V times I, but also power is equal to V squared over R. So I could do it that way, where I say 3 squared divided by 10 is 0.9 watts. Another way that I could do it is I could figure out what is I. I is equal to V divided by R, which is 10 divided by 3. Wait, I'm sorry, did I do something wrong there? No, that's right. No, shoot, that's not right. No, that's right. So I have V, which is 3 volts times... Oh, I see. Come on now, I gotta catch this. It should not be 10 over 3, but 3 over 10. 3 volts over 10 ohms. Okay, you'll see that? Okay. So 3 volts times my current, which is 3 over 10, and so that's also equal to 0.9 watts. So be prepared to do a power question. Okay? The final thing that you should expect is something to do with... oh, by the way, these are also power questions, so you should be able to be prepared for something along those lines. Okay, that's going too far on this one. Something having to do with current. Let's see if I can... Oh, here we go. Number 9. This is still that same exam. Number 9, current, I, is defined as Q divided by T, the charge divided by the time. And so if I have a 2 ohm resistor with 10 volts, that means that my current is V over R. That's 10 divided by 2, or 5 amps. So I have a 5 amp current. I want to know what the charge is. Q is equal to I times T. That's 5 amps times the time, which is 10 seconds. That's going to give me 50 coulombs of charge. Okay, 5 amps is a really big current. If I have 5 amps over 10 seconds, I have a whole lot of charge passing a point in that 10 seconds. 50 coulombs in this case. Okay? That's the quiz. I think probably the hardest part are the circuits. So we could do some more circuits if y'all like, but I'll let you guide that, what you want to see. What are some other things that you'd like to see within this framework? You feel like this is easy? Are you going to do fine? It's easy if you know how to do it, right? But if you haven't had much practice, it's going to be kind of hard. I guess I'm inclined to do circuits if y'all aren't saying much. Yeah, Sonia? Let me pull that up online. I don't think I brought the 2016. Possibly. You want me to show you how to do it? So this would fall within the definition of current. That it would be one of those questions. What is current? And so the first thing you need to do is to find out what is the charge, just like we did before. But then there's an additional step. So I is equal to V divided by R. That's 3 volts over 10 ohms. That's 0.3 amps. And then Q is equal to I times T. This is exactly the same steps I did in that previous problem. That's 0.3 amps times the time, which is 120 minutes. So that's what? 36 coulombs of charge. And then to find out how many electrons, I say 36 divided by the fundamental unit of charge. So I have 36 coulombs, and I know that there are 1.6 times 10 to the minus 19 coulombs per electron. So if I want to know how many electrons, I'd say 36 coulombs divided by that. And then that would tell me the answer. It's a lot. I think it's A is the right answer. Okay? Can I answer your question, Sonia? So the answer is yes. It could be that question. That would fall within my current category, the definition of current. Other particular questions I want to look at, Brooks?
So how far, like, should we go? Like, where should we?
I don't really gauge how far I go back. I have all of my problems in different categories, so I would go back.
Oh, I just meant like, where do we stop? Like, you
Oh,
know,
on each test? Okay, yeah, I would go all the years back. Well, what you're going to look for, well, I want to say, by the way, that you won't see a circuit of this difficulty, okay? We might get to that for the exam. It sort of depends what other chapters we might come back to and do some of these types of circuits, but as of yet, we haven't done circuits of that difficulty, okay? They're not really that much more difficult, honestly, but just the way they're laid out makes them more confusing. We might come back to that. So what you're looking for example, is that you're looking for these circuit type problems like these, right? You're not doing anything with capacitance like this, where you're calculating the area or the distance or given the dimension, so you won't have any of that. Also, sometimes on the exams, you see potential things that are spread in. Sometimes my chapter 2A got bumped into exam 2. It was just sort of how the dates fell that time. So you won't see any potential. I know this isn't exactly answering your question, but you won't see a graphing problem. Technically, you could, but like it fits within Ohm's law. But I'm telling you now that won't be on the quiz. But on the exam, possibly. And you won't see resistors like these. Okay? You could, for example, see something like that. That fits within the resistance, rho L over A, just like a Jenna. Of course, I've already told you you'll see a question like that. You won't see questions like this. Okay? Jenna? I don't remember if I put any of those on there, but there could be. Okay? Those fit within those categories. Let me tell you the SI units. For current, the SI units are coulombs per second. For voltage, the SI units, that's joules per charge, or joules per coulomb rather. Right, because the voltage is an energy per charge. Resistance doesn't really have, just the SI unit is an ohm. and power is joules per second. So I'm not answering your question, but yeah, it could be on there. You should know those SI units. Tell me this is the on there. Okay, so Brooks, returning back to your question, let's look at a couple of other exams. It's hard for me to give you numbers, like I could go through and give numbers on everyone, but it's easier if I can just sort of teach you how to identify them. So here, for example, again, you're not going to have these right here, because that's the previous thing, but then you will have the circuits. So there's no ideal EMF or EMF, no terminal voltage. That's actually from chapter 4. There wouldn't be any here. I can tell this because it says terminal voltage, and you're not going to see any of that, or internal resistance, none of that. But all of these other things on this page are okay, right? I have my voltmeter question, my Ohm's law question. There's the resistivity. This is also have to do with resistance. Like if you look back at the old exams, we worked through a question like that, in fact. And here's our power question. You'll have all of those are potential questions. Okay, and then we get past it. This is chapter 4. We'll get to that, okay? Okay? Number 4? Number 5? Yeah. Number 5 looks difficult, but it's not. If you redraw it in the appropriate way. That's the hard part about number 5. So if you imagine, if I have a battery like that, that's my circuit. And now if I redraw it, I'm going to redraw it in a different way. We'll get more into this in chapter 4, where we're redrawing circuits like this, but with resistors. That's the same circuit. Notice here, I follow along. I'm going to point A, and I break into 3 separate wires. And that's what I did here. I break into 3 separate wires. And then in the top branch, I go through 2 capacitors right here. In the middle one, I just go through 1 capacitor, and then the bottom one, I go through 2 capacitors. So that circuit is this circuit. And then if I want to know what is the equivalent capacitance, well, I think that one is a lot like ones that we've done before, because I have 4, 4, 4, 4, and 4. I know that these two combine to give me a 2 microfarad. These two, 2 microfarad. And then the equivalent then will be what? What is the equivalent? 8 microfarads. So I know it looks difficult, but it's not really. It's actually, once you draw it this way, it's actually simpler than some of the others that we've done. Okay? Good question. Others that are particular? Okay, let's look. 2014, huh? Oh, you're digging deep back there. Number what or what?
I'm not sure if it was number 7 or I think it's coming on number 7.
Yeah. This one?
No, I think it was number 13.
Number 13. This one? Okay, yeah, this is one like I was talking about. We can go back and look at 7 as well. That's a good question. But here, I want to know what is the voltage across C3. I can redraw this. So I have C and another capacitor. What is the equivalent of those 2 capacitors in parallel? 2C, right. So 2C, and I have 12 volts. And I want to know what is the voltage across this one, but I know that that voltage is going to be the same as the voltage across this one. Now that big capacitor, going to have a big or small voltage? Small voltage, right? Inversely related. Is it going to be, what is going to be the value for it? 4, right? So I'm going to have 8 volts here and 4 volts here. Okay? Does that sit okay? Are y'all okay with that explanation for it?
I think it was for like what?
Okay. Let me show, let's put some numbers in it, okay? It's a good question, and sometimes you might encounter a circuit where you have to do it sort of the brute force way. Let's say that I have a circuit with 3 microfarads and 6 microfarads and 12 volts. Now, the way that I would go about finding the voltage on each of those, this is the hard way, okay? Like the more circuitous, not a circuitous way, it requires more math, is I would first find the equivalent capacitance. And this equivalent capacitance, 1 over a third plus a sixth, is 2 microfarads. And that's 12 volts. Now, I know that the charge on this is 24 microcoulombs. Q is equal to C, that's 2, times V, which is 12. 2 times 12 is 24. I also know that capacitors in series have the same charge. So this would have 24 microcoulombs and 24 microcoulombs. Anytime I get 2 quantities on a capacitor, I can find the third. V is going to equal to Q divided by C. 24 divided by 3, or 8 volts, or 24 divided by 6, which is 4 volts. So that's sort of the long answer to how do I know that it's 4 volts. But the quick answer is to say that these numbers have to add up to equal to 12. And because I have this factor of 2 difference, the 2 voltages have to add up to, the 2 voltages have to be different. What if this voltage was not 12 volts? What if it was 9 volts? What would those voltages be? Awesome, 6 and 3. It'd be 6 volts and 3 volts. You see how those two numbers, they add up to equal to 9, but they're different by a factor of 2. Or if this was 6 volts, what would they be? Not 3 and 4? 4 and 2. Awesome. So 4 volts and 2 volts. Okay? Y'all see that? That will really help you as you're going through the circuit so that you don't have to go through this whole step. Sometimes you should be prepared to go through that step, because sometimes if your capacitors aren't, portioned exactly the right way, then you might have to go through that step. So you should know how to do that. But most of the time, this little trick will help you along the way. Okay? Does that answer your question, Chloe? That's a great question. Let's go back to that first question that you asked. I think it was number 7. Is that right? Two identical capacitors are connected in series. And those two also are connected in parallel. The equivalent capacitance of the series connection, so that would be this one, CEQ, is what fraction or what amount compared to this equivalent. Well, this is C and C, and this is C and C. The equivalent for this side is going to be 2C, right? The equivalent for this side over here, let's see, that's 1 over C plus 1 over C. That's 1 over 2 over C. That's going to be C over 2. So the equivalent capacitance of this is what fraction or what factor of this? It's 1/4. That C2 is equal to 1/4 of 2C. See? Okay? So, like, as I see it, as I saying the different categories, this could be a question that would be about circuits, but qualitative, not quantitative. Both of those questions are qualitative questions. So you should be prepared for similar ones on the quiz tomorrow. Okay? What else, y'all? You look excited to be here. Are you? Not really. Like, you don't hate having this quiz tomorrow, is that right? Is it a tough week? Organic exam? No. What do y'all have? Nothing? Just a long day. Okay. All right. What else? I'll answer questions, or we can adjourn, but I prefer to answer questions. Yeah, okay, Logan, and then Tristan will get you.
Can you give some more examples of like current stuff like that?
Current, yeah, sure. So I bet there's one in this test. They're in every test, frankly. So this is spring 14. Okay, so I don't know who asked about units, but current has units, coulomb per second. Here, I want to know the current. This is like V equals IR. You'll have one of those too. I is equal to 12 divided by 3. That's 12 volts over 3 ohms. V over R is I, so that'll be 4 amps. The conventional direction of current is, oh, for this previous question, gosh, what would the conventional current be? Clockwise or counterclockwise? Clockwise, right? Goes in that direction. It's the direction that protons would flow. All of these are good examples of these questions. In fact, if you look back at the old test, you'll see that they're very similar ones. Number 22 is not what you were asking, but this has a power question, so let's look at it. Which of these has a greater resistance, an incandescent light bulb or a bathroom heater? Now, one thing you need to know about household circuits is that the voltage is constant. I mentioned that in class. And so if I want to know which has the greater resistance, I look at this relationship, V squared over R, because one of these variables is constant. In this case, V is constant. And so I want to know which has the bigger resistance. If R is big, that means the power is small. So the one that has the greater resistance is the one with the smaller power. That would be the light bulb. You can think of heaters. They have a really small resistance, so they allow a lot of electrons to flow through. You can go. It's okay if you need to go. The electrons flow through at a much faster rate, so they just deliver a lot more energy. Okay? Let's look at this one right here, number 25. This is often trips up people. Here, wire A has 4 times the area and twice the length of wire B. Now, this would fall into like that resistivity category. Defining resistance, R is equal to rho L over A. Here, I want to know how their resistances compare. It says wire A has 4 times the area, and twice the length. So that means it's going to have half the resistance of wire half the resistance of wire B. So RA would be half of RB. This one would have the smaller resistance, and this would have the bigger resistance. Okay? Look at those. There are lots of those in the test. So practice those different types of questions where you're looking at the relationship between R, rho, L, and A. This is a current one like you asked for. The current, this is the total charge. I have the current, which is right here. I have T, and I want to know the total charge. Q is equal to I times T. That's based on my definition of current, Q over T. So I have 0.1 times 20. Remember, amps is a coulomb per second, so it gives me 2 coulombs. A is the right answer. Okay? You'd ask for current, right? But a lot of these are current. Okay. Oh, Tristan, you had a question?
My question was pretty much answered. I was going to ask about the equation relating resistance to like length and area, but we just did one.
Okay.
I was wondering if it was limited to just figuring out what the material of the wire was, or if you had other questions involved with it.
Yeah, possibly. So you will get a question with the table, so be prepared for that. But then I'm pretty sure I also added a question that's something similar to this. I don't remember for sure, but it's been about 6 hours since I made the quiz, so my memory's not that long. Okay? I'm pretty sure I added a question like that. What are y'all going to make? That's my question. What are you going to make on the quiz tomorrow? Huh? 100%. Thank you. Right? It's important. These quizzes, they add up like exams. They count as an exam in the end. It's just each quiz is like a quarter of an exam. Okay? All right. Well, that's all I have. Y'all have a great day. I appreciate you.